Okay, so up to the last slide, we have seen that partition function is one of the most important quantity in statistical thermodynamics. Now, let us see how partition function is related to various thermodynamic quantities. So, today what we will see is a rule. I need to use the red.
Data.
Red. So I have to press this and then wait. Huh?
Keys.
Okay.
Press no.
No, right. So can we start again from the beginning? Hmm?
You continue.
Okay. So I'll start from now. Okay. Okay, so far we have seen that partition function is a very important quantity, perhaps the most important quantity in statistical thermodynamics. So now we'll see how partition function is related to various thermodynamic quantities. So today's topic is partition function. And thermodynamic quantities. So, if you see here, so you have two things, one is partition function and the other one is thermodynamic quantities. If you recall partition function, so partition function Q was sum over I e to the power minus epsilon I by kT, where K was the Boltzmann constant, epsilon I was the energy of ith state. So partition function Q is nothing but giving you the microscopic information of the system. And thermodynamic quantities, for example, G, total energy, potential energy U, Helmholtz free energy, enthalpy, even volume, and so on and so forth, are the thermodynamic quantities. So today we are basically trying to link the microscopic Q with the macroscopic quantities G, U, A, H, V, and so on and so forth. Okay, so to start with, let's see the relationship between U, the potential energy of the system, as a function of partition function. Thus, the first relation between partition function and thermodynamic quantity we will be looking at. Now, as you have seen that total energy of a system was sum over Ni epsilon I. If the total energy of the system is the internal energy, so you can that means there is no external force, we can replace U with total energy of the system, which is the internal energy U. So we will relate U with Q. Now, if I expand this, I write epsilon I, and for Ni I will make use of the Boltzmann distribution law, which is N by Q e to the power minus epsilon I by kT. If we write in a simplified form, so this turns out to be epsilon I e to the power minus epsilon I by kT. Now, you also know that Q is okay. I'll make better use of the board. So you know Q is equal to sum over I e to the power minus epsilon I by kT. So what is, if you take the differentiation of q with respect to t. In other words, we want to find out dq by dt, what will it be? So, if you differentiate q with respect to temperature here, so what will you get? You get minus 1 by kt square epsilon I. So, you get minus 1 by kt square, k and t square are constant, so they come out. You also get epsilon I, that does not come out, so it stays there, and you get e to the minus epsilon I by kt. From here you get sum over epsilon I e to the power minus epsilon I by kt is equal to minus kt square dq dt. And previously we got u is equal to n by q sum over I epsilon I e to the power minus epsilon I by kt. So, now if I put this up here, we get u is equal to minus n k t square by q dq dt, which you can also write as minus n k t square del ln q, or we are writing d, right. So, d ln q by dt. So, this is the expression, or this is the relationship between the thermodynamic quantity u with the microscopic quantity or statistical thermodynamic quantity q. Let us also look at the relationship between entropy. So, we want entropy S as a function of partition function. So, this is number 2. If you recall, in few slides before, we have written entropy from the Boltzmann-Planck postulate. We have written S equal to nk ln q, plus we had written I think we had written kbe. Yes, we had written k beta e. This is the expression we had written before. Now, again, if we assume that there is no external force on the system and the total energy of the system is nothing but the internal energy, so we can replace this E with U. So, we can write entropy as S is equal to nk ln q plus k and beta. So, k and beta is equal to 1 by kt u. So, nk ln q plus 1 by t, and u is u we take from this expression. So, if we put it back, so we put it back, we had if we put it back, we get nkt. Okay, we have a minus nkt because we have a, so this k gone, and this t, that t, one of the t's will gone. So, we have nkt d ln q by dt. So, this is the relationship between S and Q. So, here we have the thermodynamic quantity entropy, and the microscopic quantity is appearing in both terms in the right hand side here and also here. So, this is the expression we got for entropy. Let us go to other important thermodynamic quantity like A. A, as you know, is a Helmholtz free energy, and A is U minus Ts, as you learned from thermodynamics. So, U minus T and S we got from the previous slide. We got Nk ln Q plus we got U by T. So, if we simplify, we get U plus Nkt ln Q minus U. So, this goes this should be minus. So, we got A is equal to minus Nkt ln Q. This is the expression between Helmholtz free energy A with partition function Q. One thing I just want to point you out that I think in some of the previous slides I had used small n, and here I am using capital N. They represent the same thing, the total number of particles. So, small n or capital N are the same. They are the total number of particles. What will be the pressure of the system? So, this is number 3, relation number 3. Now, we will be looking at the relation number 4, which is the total pressure of the system. Again, pressure is also important thermodynamic quantity, and again from your thermodynamic equations you got pressure as minus del A by del V at constant temperature. This relation I am sure you have seen in your thermodynamic part. So, the pressure will simply be, since we already have A from here, so we can put it there, and we get A is equal to plus Nkt del ln Q by del V at constant temperature. This is the expression for P in terms of partition function Q. So, essentially all these expressions are saying that if you can somehow get the partition function, if you can calculate the partition function or how the particles are distributed across the energy states, then you can easily get all the thermodynamic quantities of your interest. Okay. So, these are some general relationship. Now, let us take a special case, and in here we will be finding out the partition function of a monoatomic gas. So, that is our next topic.